Force on a current carrying conductor in a magnetic field. When we place a current carrying conductor in a magnetic field, it experiences a force, and the equation for the force is given as I multiplied by L cross B. This is not just times, it's cross product of two vectors. And L cross B is magnitude of L, magnitude of B times sine theta. So we have it that if we replace this with L cross B here and rearrange it, we have BIL sine theta, where B is the magnetic flux density in Weber per meter square or Tesla, and I is the current in the conductor, L is the length of the conductor, F is the force the conductor experiences in Newton, and theta is the angle between the conductor and the field. You see, the direction of motion of this conductor, the direction of the force, can be determined using the Fleming's left-hand rule. And this is the Fleming's left-hand rule, that if we have our thumb, the forefinger, and the middle finger held out at 90 degrees to one another, and the forefinger pointing in the direction of the field, and this is what we're trying to say. You see, this is the direction of the field, and this is the direction of current. You can see the current moving outward here. Then the force moves upward in this manner, meaning that the force on this conductor is acting upward. This is the direction of the force. This conductor will move upward. The field, interaction between the field and current, throws it upward. That's what we are trying to say using the Fleming's left-hand rule. So that's that about that though. Now let's look at example 1. A 20 cm wire carrying a current of 10 ampere and placed in a uniform magnetic field of 0.3 Tesla. If the wire makes an angle of 40 degrees with the vector B, find the magnitude of the force on the wire. So let's solve this question. The first thing is that we are given the length of the wire, 20 cm. I just need to divide by 100. That's 0.2 meter. And next, we are given the current, 10 ampere. And we are told that the magnetic field is 0.3 Tesla. And that the angle between the wire and the field is 30 degrees. So we're going to say F is equal to BIL sine theta. And that's 0.3 times 10 times the length, 0.2, then times sine. So the angle is 40 degrees, not 30, so 40 degrees. So this will give us 0.386 Newton. That's the magnitude of the force. Example 2. A wire carries a steady current of 2.5 ampere. A straight section of the wire with a length of 1 meter along the x-axis lies within a uniform magnetic field. B is equal to 2.0 K Tesla. What is the magnitude? What is the magnetic force on the wire? Okay. So to solve this question, let's write out the parameter given to us. First, we are given the current in the wire, on the wire. And that's 2.5 ampere. And then we are told that the length of the wire lies on the x-axis actually. So that's 1I. I for the x-axis. And the magnitude is just 1 in meters. And the next is the magnetic field, B, which is 2.0 K Tesla. This is in meters. Okay? I, to show it is in the x, in meters. So the next thing we're going to do is to say that F is equal to I, then L cos B. Okay, so that will be 2.5 into brackets 1I cos 2.0 K. This is 2.5. 1 times 2 will give us 2 times I cos K will give us minus J. So that is times minus J. So this is like saying minus 5.0 J for the force in Newton. Another way to do this is to do your L cos B using matrix. L cos B, write out your L. This I, J, and K. Write out the L first. For the length, it's just having 1 in the I, no J, and no K. And for the B, it's having no I, no J, and just 2K. And so if you do I, your I, you know this plus, minus, and plus. If you do your I, this is 0 minus 0, because cover here, get this times this, and minus this times this. If you do your minus J, cover here and cover here, you get this times this, 2 minus 0. And then if you do your K, cover here and cover here, get this times this, 0 minus 0. That's what you will have. So at the end of the day, it's just minus 2J. And that's exactly what we have here actually. So that's that for this question. Torque on a current loop. You see, if we have a rectangular coil as shown, and current flows through this coil, and this coil is in a magnetic field, then there will be motion on this coil. And let's analyze why the motion would occur. Now understand that, let me assume that current flows inside this conductor inward like this and goes like this. So the current here comes outward this way. Now, if the current goes inward this way, then this direction of current here, going in this manner, this direction of current, going inward. Now, understand that using Fleming's left-hand rule, this is it. This is the direction of the field, this is the direction of current, and this is the direction of force. On this part of this coil, there will be a downward force. So hence, this side of this coil is pulled downward. And now, on this part of this coil, the current direction is like this. Still following Fleming's left-hand rule in this manner. The direction of the current, direction of the field again, and direction of force upward in this manner. So this part is lifted upward. Now these are two parallel forces. And because of that, this coil will turn like this. If the coil was like this, let me illustrate using a book. Now, if the coil was like this, the coil will move like this. And so there will be a torque. And so that's what we are looking at. So many things work on the application of this principle. We have galvanometers, we have motors. They work based on this principle that current moves through a coil in a magnetic field. Now we have it that the torque on this magnetic field is giving us B, the magnetic field, the flux density times current, times the number of turns in the coil, times the area of the coil, then times sine theta, where theta is the angle between the plane of the coil and the magnetic field. So let's take this question now. A vertical rectangular coil of side 5 cm by 20 cm. So solution. The area will be 5 cm times 20 cm. And that will be 100 cm square. But we need to convert this to meter square. So divided by 100 square. And this will be 0.01 meter square. Okay? Has 10 tons. So number of tons is 10. And carries a current of 2 ampere. So I is 2 ampere. When placed in a uniform magnetic field of 0.1 Tesla, so our B is 0.1 Tesla. Okay? So now, we are asked to calculate the torque. We're not given angle here, so we assume we are getting the maximum torque because if there's no angle, the angle is 90 degrees. We have maximum torque. So BINA is our relationship. The B is 0.1 times I2 times number of turns 10 times the area 0.01. So if we do this, we are going to have 0.02 Newton meter. That is the torque. Galvanometers and motors. These are devices which work on the basis of current flowing in a coil placed in a magnetic field. A galvanometer measures small electric current, and it can easily be modified into a voltmeter by connecting a resistor in series with it, and also be converted to an ammeter by connecting a shunt into it. You see, electric motors are devices which convert electrical energy into mechanical energy. Force between two parallel conductors. First of all, one thing I want to say is this, and we must know, is this. If there's a current in a conductor, there will be a magnetic field in that conductor. So current generating magnetic field. And if there's a magnetic field in a conductor, current will also be generated. So if there's a magnetic field, current is generated. And if there is current, magnetic field is generated. Now, you see, let me assume there's a current flow in this conductor. A magnetic field will be generated around this conductor. Now, this magnetic field extends to this conductor. Hence, there will be a magnetic field in this conductor. As a result of this magnetic field, it extends to this conductor. And because of that, this conductor will now exist within the magnetic field of this conductor. Now, if that be the case, there will be a current on this conductor as well. Why? Because there's a magnetic field there. Let's say this magnetic field here is having magnetic field of flux density B1, for instance. Then we see there will also be a current. The current here, now let's call it I2, for instance. Let's say the current here was initially I1 that generated this magnetic field. Now, because of this magnetic field, a current is now generated here, and that current is B2. We can then say that the force on this conductor will be F equal to B1, which is the field of this, then times I2 times L. But we've said initially that the magnetic field on a coil, on a long conductor or a wire, is giving us U naught I over 2 pi, the distance to the field. Hence, if we substitute that here, this is going to be U1 actually, because this is B1 for this one. Hence, the force experienced by this second conductor will be U naught I1 over 2 pi d, then times I2 L, which is the length of the second conductor. Now, most often, we love leaving our answer, our value as force per length. In that case, the force per length, which I can call F prime, which is force per length, is actually giving us U naught I1 I2 over 2 pi d. And this is the distance between the two conductors. So that's the relationship for the force per length, or just for the force. Let's take example on this now. Example 1. What is the magnitude of the force per length of each pair of conductor of direct current line carrying 10 ampere each and spaced 10 cm apart? Well, the first thing, let's set out what we are given here. We are given the current, that's I1, which is I2, 10 ampere. And then we are given that the distance between them is 10 cm, which converted to meter will give us 0.1 meter. Okay? So let's calculate now. We know that our U naught actually is giving us 4 pi times 10 raised to the power minus 7. Okay? So with this now we can say that our force per length is given as U naught I1 I2 over 2 pi d, which is 4 pi times 10 raised to the power minus 7 times 10 times 10 divided by 2 pi times 0.1. This will give us 0.0002 Newton per meter. That's the answer for this question. So we want to look at all effects. In 1879, Hall discovered that when a magnetic field is applied perpendicularly to a current carrying conductor, that a voltage is developed across the conductor. The direction of the voltage is perpendicular to both the current and the magnetic field. You see, this voltage is known as the Hall voltage, and this effect is known as the Hall effect. You see, the Hall voltage is given by the equation Hall voltage is equal to the magnetic flux density times velocity times the width of the conductor. But we know that the drift velocity or velocity is given by the equation I current over area times number of charge carrier times the charge on an electron. If we substitute that for velocity here, we have that our Hall voltage becomes B multiplied by I over area times number of charge carrier times charge in electron, then times D, which is the width of the conductor. Now, again, this will give us B, I, D, area, and QE. But, you see, area is the length times the width. If we do that, this will give us that the Hall voltage will then be B, I, D over length times width, number of charge carrier times E. This will eliminate this. So this becomes the Hall voltage. So this is our Hall voltage, equation for Hall voltage. Any of these, either this or this. So let's take an example under this now. A sample is 20 mm thick and placed in a 0.8 Tesla magnetic field, producing a Hall voltage of 0.2 microvolts, which carries 15 ampere current. What's the number of the free electron? So we're looking for N. So what are we given here? Firstly, we are given the magnetic field, 0.8 Tesla. This is magnetic flux density. Next, we are given the thickness, which is the length of the conductor, 20 millimeter, 20 mm. That's divided by 1000, will give us 0.02 meters. Okay, next, we are given the current. And the current here is 15 ampere. And lastly, we are given the Hall voltage, which is 0.2 microvolts, and that's 0.2 times 10 raised to the power minus 6 volts. And we know that the charge on an electron is 1.6 times 10 raised to the power minus 19 coulomb. So we want to calculate the number of free electrons. We know that Hall voltage is equal to B, I, all over the equation we have there, and charge on an electron times the length. If you make N sort of formula, we'll get that N is equal to B, I over all the Hall voltage times charge on an electron times the length, which we can call the thickness. Our B here is given as 0.8 multiplied by the current, which is 15, divided by the Hall voltage, 0.2 times 10 raised to the power minus 6, times the charge on electron, 1.6 times 10 raised to the power minus 19, then times the length, which is the thickness given the question, and that is given as 0.02. So let's evaluate this now. This will give us 1.875 times 10 raised to the power 28 electrons, or charge carriers. So that's that for this question.